This is Dr. P. Jaikanth Yadav, working as assistant professor in the Department of Mathematics at Institute of Aeronautical Engineering College, Hyderabad. My course title is Complex Analysis and Special Functions, and today my topic is complex line integral along closed path. So I already discussed in the previous classes what is complex line integral, and today I am going to do the complex line integral with closed path. So today we will take closed path. This is the first problem in the line integrals along closed path. Here in this problem, evaluate the line integration over C z square dz, where the curve C is the boundary of the triangle. We know the boundary of the triangle is closed path with vertices 0, 1 plus I, minus 1 plus I. So here we have to observe that we have to take integration along the clockwise direction. So now if you see here, I am drawing this boundary in complex plane. Here it is there is a point. This is the z is equal to 0, and this is I am taking z is equals to 1 plus I. Here I have to take another point which is z is equals to minus 1 plus I. So I have to connect all these points so that I am going to get triangle. I'm going to get triangular path. So this point I am taking as O, and this point I am taking as A, and this point I am taking as B. So here we need to perform integration in the clockwise direction. That's why I started at O, and I am moving to B. Then I am coming to from B to A, then A to O. So this is a real axis and this is imaginary axis. We already know x and y are real numbers. So on this path, on YA path, the y and x and y having the relation y is equal to x. This we can get by taking a line equation from 0, 0 to 1, 1. Then we can get y is equal to x. And similarly, we need to identify this path, AB path, B to AB path. So this is nothing but y is equals to 1. Y is equals to 1. And the path OB, this path mathematically you can write as y is equals to minus x. In this problem, we have to perform integration in this closed path. Okay. So when we are performing integration along this closed path, we can write integration over C z square dz. We have to evaluate, and we know this triangular path is C. So this I can write it as integration from I have to start with O, and then I have to move B, A, then O. Z square dz. So integration along this triangular path, I am going to split into 3 parts, which is integration OB z square dz plus integration BA z square dz, then integration along AO z square dz. So will give an equation numbering for this. Writing equation number 1. Now I am going to do this is a part 1. I will I will do this one as a part 1, integration evaluation of this integral, and this integral is I'm considering as part 2, and this will be part 3. I'm dividing this whole entire evaluation of these 3 integrals as 3 parts. So first one, in the first part means evaluation of integral along OB. So along OB, so the path of OB, is y is equals to minus x. Okay, whenever y is minus x, then dy becomes minus dx, because I am performing derivative on both sides. So I will get this expression. So that what is dz? Dz we know, which is dx plus I dy, but here we know dy, that's why it is dx minus I dx. It is nothing but 1 minus I times dx. Okay. Now I am going to evaluate the required integration OB of z square dz here along OB. Here z is z is x plus iy whole square, and dz we already calculated, and I'm also writing here also dx plus I dy. Right. Now I'm going to use this one, y is equal to minus x and dy is equal to minus dx here. So I will get integration along OB x minus ix whole square, and here I can take dx minus I dx. Now integration along OB, here I can take the x square 1 minus I whole square, and here 1 minus I into dx. It is observed that here the integration comes in terms of x. The integrand comes in terms of x. Along OB at O x value is along O at x value is 0. At B x value is minus 1. This we have to observe. So I am writing now at OB at O x value is 0, and at B x value is minus 1. And we are having 1 minus I whole cube x square dx. This. So we will calculate this integral value now. Here you will get 1 minus I whole cube. Here you will get x cube by 3, and x variation from 0 to minus 1. So this is simply minus 1 by 3. Here it is do the binomial expansion for 1 minus I whole cube. You will get 1 cube minus 3 into 1 into I, next plus 3, 1 into I square, next minus I cube. Here you will have minus 1 upon 3 and 1 minus 3I, next to minus 3, because I square is minus 1. Next to minus I cube. I cube is I square times I. I square is minus 1 into I is there. So this becomes minus I. So minus of minus I. So So in this case, in this way you will get minus 1/3, here minus 2, minus 2i. In this way you will get 2/3, 1 plus I. That is integration along OB of z square dz value is 2/3 of 1 plus I. We'll make it is equation number 2. Okay. Now we have to perform integration along. We will do second part along BA. Along BA. How we can represent mathematically this expression, this curve? This curve we can express mathematically by y is equals to 1. So we will write here along BA, we can write y value is 1. So dy value becomes 0. Here you can observe that y comes in terms of y will be constant, dy is 0. So in z square dz there will be no y. So only we will have x. Along BA, how x is varying? Here x varies from BA. At B you see real part is minus 1. At A real part is 1. That is x variation. So x variation from minus 1 to 1. Now you calculate along BA z square dz. This I am writing BA along BA x plus I y whole square dx plus I dy. Okay. Now y is 1 here, right? Do now. Here it is integration from b to a. It becomes x plus I whole square and dx only, because dy is 0. Okay, because dy is 0, that's why you will have only dx. Now integration, see we are getting integrand in terms of x. Now we will write from minus 1 to 1. Here I will write x square plus I square plus 2i x dx. Now we will have minus 1 to 1 x square minus 1 plus 2i x dx. This is integration from minus 1 to 1 x square minus 1 dx plus 2i integration from minus 1 to 1 x dx. This integral value is 0 because this is odd function. Integrand is odd function here. Okay, that's why this integral value will be 0. Now we have to evaluate only first integral. So in this case, and we have it is even function. So I can write it as integration from 0 to 1 x square minus 1 dx. So it is 2. I'm going to evaluate this integral value and we will have 1 by 3 minus 1. 1 by 3 minus 1. Okay. Now you are having it is minus 4 by 3. So what is that is integration along BA of z square dz is minus 4 by 3. This is equation number 3. Previously we given equation 2 and this is equation number 3. Now we will evaluate. Now along AO, what is y? Y is x only. Next, you can see here along AO, y is x only. This path we can represent as y is equals to x. So it is a derivative of y will be dx only. Okay, so that dz will be 1 plus I times dx. Okay. Now here in all the y comes in terms of x and dy also comes in terms of x. So we can check how x is varying. Here x varies from 1 to 0. Along AO you can identify x variation is from 1 to 0. Therefore, we are calculating integration along AO z square dz. This is integration along AO x plus I times x, because y is x here, that's why, whole square, and we will have dz is 1 plus I dx. Now we can write it as integration along AO x square 1 plus I whole square, here 1 plus I dx. Now you can observe that it is 1 plus I whole cube, integration from C, which is comes in terms of x. That's why I am taking from 1 to 0 x square dx. Now you expand this. If you expand this, you will have 1 plus 1 plus 3i. It is minus 3 minus I, the binomial expansion of 1 plus I whole cube. Here you will get second integral value is minus 1 by 3. Now simplify this, you will get minus 2 plus 2i, and it is minus 1 by 3. It is nothing but 2 by 3, 1 minus I, 2 by 3, 1 minus I. So this is what, that is integration along AO of z square dz is 2/3 of 1 minus I. This is equation number 4. Adding equation 2, 3 and 4, we get integration along C of z square dz is equals to, from equation 1 we have 2 by 3, 1 plus I. 2 by 3, 1 plus I. From equation 2 we have minus 4 by 3. Next, from equation 4 we have plus 2 by 3, 1 minus I. If we add this sum, we will have, it is 0. we are getting here 0. So in this problem, what we have done is that we are performing integration along the closed curve. That closed curve is triangular path. And we have in this problem, we have 3 sides. For each side, we have different mathematical expressions to represent curve. So along these 3 paths, we calculated integral, and we have summed it. We have added these 3, and we are getting the integration along whole triangular path, and we are getting the result is 0. Okay. Next problem is this. Here, you have to prove that integration along C 1 by z minus a dz value is 2 pi. And second one here, the second part is integration along C z minus a whole power n dz value is 0 for any integer which is not equals to 1. This equality is true. Second one is true. Here, the curve C is given as circle. It is given circle. What is the center of the circle? Center of the circle is A. In the complex plane, it represents a circle whose radius is R and center is at A. So if you take it is in complex plane, and suppose it is z is equals to A. So in complex plane, horizontal axis is the real part, and the imaginary axis is also real. That is y. Reference by y, we represent it is y, and it is z is equals to A, and it is a circle whose center is A and the radius is R. This is nothing but C, our curve C, and which is modulus of z minus A is equals to R. So I will write this problem whenever we have the integration along the circular path. We generally use parametric form. Whenever we are performing integration along the circular path, we generally use parametric form. Now we will write the parametric form. The parametric form of the given circle C is z minus A is, we can write, this is the parametric form, z minus A is equals to R e power I theta. Here parameter is, what is the parameter? Here the parameter is theta. Here this parameter variation on this curve. Parameter variation on this curve is where theta lies between 0 to 2 pi. So I know this relation. Now I can write what is z. Z is A plus R e power I theta. So derivative of z becomes derivative of A plus R e power I theta. For the first derivative of R is 0 plus next we have R e power I theta into I into d theta. That is dz is I R e power I theta d theta. This is required for us to perform the integration. Now I am going to do first one here. So integration along C 1 by z minus A dz. So integration along C 1 by, what is z minus A? Z minus is R into e power I theta. And what is dz? Dz is I times R e power I theta d theta. So if you observe this R e power I theta is there in the both numerator and denominator, you can cancel it out. We will have I is there in the integrand, we can take it out from the integral symbol. So it is integration along C d theta. Along C, how theta is varying? How theta is varying along C on the curve C? We are writing in the parametric form. In the writing of parameter form, we already mentioned theta varies from 0 to 2. So it is I integration from 0 to 2 pi d theta. And you know I, here it is theta, and theta we have to take 0 to 2 pi. So this we will get I 2 pi minus 0. This is nothing but 2 pi I. Okay. So this is the result. This one. So first one is proved. And we go for the second one. So second part. Here it is integration along C. We already know z minus a taken as r e power I theta whole power n. And what is dz? It is I times r e power I theta d theta. Okay, so I will do just so I have to evaluate integral along C z minus a whole power n dz. So integration along C, it is r e power I theta whole power n, and dz is r I e power I theta d theta. So I can write it as, now it is r power n plus 1, r power n plus 1, and integration along C e power I times n plus 1 times theta. N plus 1 times theta. So there is I also here. You can observe. There is I also in the integrand d theta. So I and r are independent of theta. So that's why we can take from the integrand, from the integral symbol. That is, there is I r power n plus 1 integration along C e power I times n plus 1 times theta d theta. Now, if you see integrand comes in terms of theta, along theta, along curve C, how theta is varying? It is varying from 0 to 2 pi, I times r power n plus 1. Their integration from 0 to 2 pi, e power I times n plus 1 times theta d theta. If you perform integration, what we will have? I r power n plus 1 e power I times n plus 1 times theta by I into n plus 1 we will get. Here how theta is varying? Theta is equal to 0 to 2 pi. Now you can observe that I is there and here also I is there. I gets cancelled. And here you can get, it is r power n plus 1 by n plus 1. R power n plus 1 by n plus 1. And here you can get, it is e power I times 2 pi n plus 1 theta. It is minus e power 0. E power 0 is 1, we already know. So it is r power n plus 1 by n plus 1. And here you can get, it is cos of 2 pi n plus 1 theta plus I times sine 2 pi n plus 1 times theta minus 1, because e power 0 is 1, and e power I theta I am writing by Euler's theorem. We know e power I theta is cos theta plus I sin theta. That formula I have used there. So here I can get r power n plus 1 by n plus 1. Here I can get minus 1 power 2 times n plus 1. Here it is a sign multiples of pi. Sign of multiples of pi is always 0. 0 minus 1. Okay. Now it is r power n plus 1 by n plus 1, and this we will get 1 minus 1, and this is r power n plus 1 by n plus 1 into 0. This is 0. Okay. 0. Now you can see the second integral, we take an integration along C. Here integrand is z minus a whole power n, and we taken parametric forms. So we calculated this, and finally we shown that it is 0. Here Euler's theorem, we are writing exponential e power I times 2 pi into n plus 1 theta. That we are writing in terms of cos plus I sin form. Okay. So cos of pi multiples, we know the formula cos n pi. Cos n pi is minus 1 power n. Similarly, sin n pi is always 0 for every integer. For every integer, this is. We have used this 3, and we shown that this result. Okay. So this. So thank you. So these are the references for this lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.